Everything that went wrong today, we're on time. Amazing. Between somebody taking our room and there being a late pizza and stuff. So thank you guys for being adaptable and for coming and finding space where you can in our office here. If anybody needs more chairs, let us know. We can pull some more around. Sit on the sides as well. Hi, I'm Fidela Saunders. I'm the editor-in-chief of Scientist Magazine. I also work with the RTP chapter of Sigma Xi, who co-sponsors our events, along with Science Communicators of North Carolina, who help us book our speakers, and North Carolina Biotechnology Center, which provides our pizza money. So thank them very much. So this is Science by the Slice. We run this during the academic year, so we will be taking a summer break. And so our next talk will be in September. So keep an eye out. If you are not signed up for emails, you can do that actually through the NC Biotech website. There's a place to do that, or you can just let me know. And so we'll be back in September, but in the meantime, if there are other interesting events during the summer, keep an eye out. I will send those out to people who are in Sigma Xi and through other channels. Couple of quick announcements. Sigma Xi. Okay. Sigma Xi is running a science policy boot camp over the summer. So if you are a scientist who has been interested in learning more about how lawmakers use policy or how you can become an expert to advise lawmakers, this is a really cool boot camp. This will be the third or fourth year they're doing this one. It is up on the Sigma Xi website. It is held in person. So it's specific to this location. The other event that's coming up is the I4 conference, the International Forum on Research Excellence, which is virtual this year. That program is about to go live. It's a very cool conference, a lot of good speakers, so no travel required. So you guys, if you want to join in, I know we've had some local members put in for sessions, so you might see some of your local people in the program as well. So please keep an eye out for those events. But today, for Science by the Slice, we're really excited to have Dr. Kate Scholberg, who is the Arts and Science Distinguished Professor of Physics and a Bass Fellow, at Duke University. Her broad research interests include experimental elementary particle physics, nuclear physics, astrophysics, and cosmology. Her specific interests in neutrino physics lie at the intersection of these areas. Scholberg is a member of the Super Kamiokande Tokai to Kamioka T2K, sorry, I can't read it, and the Deep Underground Neutrino Experiment, DUNE, neutrino experimental collaborations. She is the spokesperson of the Coherent Experiment, a neutrino scattering experiment located at Oak Ridge National Laboratory, and a co-founder of SNEWS, the Supernova Early Warning System, a global network of neutrino observatories. She received her bachelor in physics from McGill University in Montreal and a PhD in physics from the California Institute of Technology, and she's been at Duke since 2004. So thank you very much, Dr. Scholberg, and we look forward to your talk.
Yeah, thanks. Thanks for that introduction, and thanks for having me. There's nothing I love more than talking about neutrinos. So always fun. So I'm going to tell you how to see a star explode from underground making use of neutrinos. So what are neutrinos? Neutrinos are elementary particles. They're known as the ghostly particles. They are basically they go right through things. I'll talk about more about that in a bit. And what we're after in the big picture, and why we care about neutrinos, is they're part of the big picture. They're basically part of the understanding of nature, the nature of energy and matter and space and time on both the largest and smallest scales. What we really want to know is, what are the fundamental particles that make up the universe? And we know that neutrinos are some of these fundamental particles. How do they interact with each other? What are the forces that govern how they handle each other, how they interact? And also, how did the universe come to be the way it is? And that depends crucially on these other two questions. So of course, these are gigantic, huge questions. Neutrinos are just part of it, but they may have big impacts. And so about that big best picture, we have something in particle physics that is called the Standard Model. And these are the fundamental particles in cupcake form right here. So we have the quarks, which are the particles that make up nuclei. So actually these ones right here, these quarks, up and down quarks, make up protons and neutrons, which are in nuclei of atoms. And then the leptons, the familiar one that you really know about is the electron is also part of an atom. And so these are the ones that are, familiar from high school chemistry, from high school physics, these quarks and leptons. But there are actually more of them. There are these other ones. There are these quarks, which are heavier. There are also particles that actually, they're called force mediators. They are basically required in order for the particles to talk to each other. They basically exchange between these other particles in order for them to interact with each other. And the neutrinos are here. They're leptons. They're actually cousins to these other particles. There's the electron, which is the charged lepton. It has electric charge. This is the one that everybody is familiar with. But the electron has heavier siblings. A muon is about 200 times heavier than an electron, and a tau is many times heavier than that. These are kind of like heavier versions of electrons. And then there are these three, we call them flavors of neutrinos that are basically the siblings of the charged lepton. So we know we have these neutrino particles that are part of, they're among the family of fundamental particles. And they're actually very weird. They have very, very strange properties. One of the very weird properties is that their mass, and we actually now know that their mass is extremely tiny. Actually, I gave a talk, Signal Sci talk 20 years ago, and it was actually about how we know neutrinos have mass. So we've actually known that for now something like 25 years, more than 25 years, that neutrinos have not zero mass, but some very, very tiny mass. We actually don't know exactly what it is. And this is just an illustration here. This is an electron. Now, you know that electrons are very light. They're like 2,000 times lighter or thousands of times lighter than their nuclei that they live in. They really are only a tiny part of the mass of an atom. So we think of electrons as actually being very light particles. But neutrinos are even much, much lighter. They're less than 500,000 times smaller. Their masses are less than 500 times the mass of an electron. So they're really tiny. So this is actually, I actually figured out the approximate ratio of an elephant and a mouse. And a neutrino is basically the mass of a neutrino compares to that of an electron, which is a light particle. So these are really, really light particles. And we actually don't know why. That's a very strange thing. We know in the standard model, the kind of picture of how the fundamental particles interact, what they are and interact, is that there are actually the standard model doesn't include all of these. The standard model actually only includes 3 of these. Gravity is actually another question. But these are the 4 fundamental forces that we know about. There's a strong force, which keeps the quarks together in nuclei. There's the electromagnetic force, which you're all familiar with. It's kind of the force that you deal with every day when you touch things. And then there's the weak force, which is a bit of a weird one. It's a force that actually is involved in various radioactive processes. It's involved in what causes, or how the sun produces energy, things like that. So this is maybe a more subtle one. And it's very weak, and it's called the weak interaction for a reason. Now, neutrinos interact only by the weak force and gravity. We know they do interact by gravity, a tiny amount because they have small mass. But the weak force is weak, and what that means is it will hardly ever cause an interaction. If something interacts only weakly, it means it will usually just pass through things and almost never leave any trace, never make an impact, never hit anything. And that's what we mean when we talk about a weak force. And if you consider a regular particle like a photon, a gamma ray photon is essentially a particle of light related to the electromagnetic interactions. Gamma rays are forms of radiation. They're actually super high energy photons, and they are actually famous for being very penetrating. They're used in radiotherapy, for example, and it can go actually through something like a big chunk of carbon. A high energy gamma ray could go right through it and get to the other side. Alpha particles and beta particles are actually electrons. They can go through also layers of matter, but less. A gamma ray tends to be very penetrating, goes through more matter. And these are not weakly interacting particles. If you have a weakly interacting neutrino, that of the same energy as a gamma ray photon that will go through 20 centimeters of carbon, a neutrino would go through an entire light year of lead before it would be likely to bang into it. Okay, so they just go right through this. And you can actually think of it, a neutrino could travel through about 100,000 Earths before it would ever even interact once. Okay, so these are really, that's what it means to have a weak interaction. It just, it will interact randomly, but only very, very rarely, so that it would tend to go through a whole bunch of matter before ever going anywhere. So it can basically go right through the Earth. And so most neutrinos just go right through you. There's neutrinos. In fact, there are trillions of neutrinos coming from the sun, and they're just going right through. They're going right through everything. They're going through the Earth. They basically hardly touch anything at all. And so you might ask the question very reasonably, if neutrinos are just sliding through things, never bumping into anything, how can you even tell they're there? And the answer is they do sometimes interact. But then this, of course, this is my era. Also, this is Star Trek Next Generation. This is Geordi LaForge. And he had a special visor that I've always been super jealous of. It was a visor that allows him to see neutrinos. Now, unfortunately, from what we know about particle physics, that does not work. Unfortunately, there's no such visor. We can, however, detect neutrinos because even though they most of the time go right through things, once in a while, they will bump into something and they will make a kind of splat, and they will dump some of their energy into normal particles that we can then see in a normal way. They can make photons, they can make electrons that we could actually detect using normal particle detectors. So this is how we can actually know that neutrinos are there. Now, because the interactions are so rare, you need either lots and lots of neutrinos, and actually that's often not a problem, or you need gigantic detectors. If you want to even intersect one neutrino, you need an enormous detector to have any chance of even having one of them bump into your detector and leaving some energy that you can see. And so the detectors that we have, many of them are really, really huge. They are kiloton scale, even approaching, some of them are megaton scale. So they incorporate enormous volumes of material as targets for a neutrino that will occasionally bump into something inside the detector and then create some energy that you can actually see. And so these are just examples. These are pictures. I'm going to talk a bit more about some of them. Not only that, the other difficulty is that on the surface of the Earth, cosmic rays, particles are coming from space all the time. And you don't feel them. But they're charged particles. They're cosmic ray muons and actually other particles. Muons are kind of heavier electrons. They're actually coming from various sources in space. Actually, it's an interesting question. Where do they come from? That's a whole field of particle physics, actually. And some is known. There's still mysteries. But on the surface of the Earth, if you actually put your hand out, there's about 1 cosmic ray muon per second going through your hand coming from the sky. Okay. So, you don't, you can feel them, it would hurt. But fortunately, you don't feel them. But there are lots of them going through, and you can see them in a particle detector. It's actually very easy to actually make a particle detector that would create a signal. You'd actually have an electronic signal every time a muon went through. And that means that if you build a detector and you're looking for very rare neutrinos to bump into something, make a signal, if you've got, in an enormous detector, if it's 10 kilotons and it's at the surface of the Earth, it's going to be constantly lighting up with cosmic rays going through it. So it's going to be like so much noise that you're going to have a really hard time seeing that one neutrino from a constant rain of cosmic rays. And so for that reason, the big detectors are usually built underground. So you put them underground where there's a big overburden of rock that absorbs the cosmic ray muons that are coming from the sky. And in fact, there's many examples. In fact, most of the pictures I showed you, and I'm going to talk about more about some of them, they're mostly deep underground because you have to shield out the cosmic rays, which will totally drown out your neutrino signal. Okay, now, so that was neutrinos and how we detect them. Now let me talk about supernovae. So supernovae are stars that blow themselves up into smithereens. They're basically energetic outbursts that results in the complete destruction and death of a star. And these are events that can be very, very luminous in photons, basically in light, actually light of many different wavelengths, that can for a time be as luminous as an entire galaxy. And a famous astronomer once took me to task for saying that. In fact, they're not as luminous as a regular galaxy, but they can be as luminous as a small galaxy. But the point is, they can be really, really bright. A supernova, star blowing up, can be really enormously bright for a short time. Now they come in different types. And this is one of my favorite tweets ever about astronomers. It says, if astronomers were in charge of naming them, pies would be called type 2 cakes. Okay, so astronomers really like to call things type 2, type 3. And supernovae are no exception. There are two main types of supernovae, type 1 and type 2. And they actually are very similar. They're both extremely bright. They kind of look generally similar. They have some somewhat different features. One of them is a thermonuclear explosion. It's basically a star that has a companion, and it gathers matter from its companion until it contracts and it gets hotter, and then it blows up. And that's a type 1a. And actually, these are actually very interesting in themselves. They're actually very useful for cosmology because they have typically uniform amounts of light, which helps to tell how far away they are. So that's a whole other story. The kind that I'm interested in this talk, at least, is the type 2. And this is the death of a massive star. A star that starts out with more than about 8 times the mass of the sun will eventually burn out its core so that its core is full of ash, and it can no longer hold up the weight of that star, and it will collapse, and then it will rebound in a giant explosion. And it's this kind of event. This actually is what creates what's called a compact object, which I'll say a bit more about in a second, which is either a neutron star or a black hole. And it's this kind that emits a giant amount of neutrinos. So this is basically the model of what happens. And actually, we have a pretty good understanding of what goes on. I mean, not in every detail, but sort of in the big picture, is that you have a star and it's burning nuclear fuel. It's running, it's nuclear fusion. It's creating the energy of the star. That's what's happening in our sun. Our sun will never go supernova, by the way. It's not big enough. But a big star will start burning heavier and heavier elements until ash builds up in the core that can't burn anymore. It actually starts to make iron, which can't burn anymore. And then when it can no longer hold up its mass, the thing squishes down. It comes to, actually, this is the technical term that the scientists, the people who study this actually use, because it comes to maximum scrunch. And it actually, what happens is it's so dense that electrons and protons actually merge together to make neutrons. So they actually make new particles, they actually squish together. And you end up with a compact ball of neutrons, and you get enormous numbers of neutrinos. And actually, if it's big enough, you can actually you can have a further level of collapse where it actually collapses to a black hole. I'll say a bit more about that. And so here's just an illustration. Neutron stars are extremely exotic, and these have been observed actually in the sky. This is an object, it's actually about the size of a city. So it's basically the entire mass of a star, of a sun-sized star. It's basically the core of the star, which is about the mass of the sun, which is squished into maybe 10-kilometer radius. Okay, so it's extremely dense. Of course, this is not a photograph. This is just to show you what a neutron star would, basically its size next to a medium-sized city. And this is a very exotic object. There's actually tons of physics we can learn from that. So it's a very, very interesting remnant. And then you can also have, if there's even more mass, the neutron star can't hold itself up against gravity. There can be a further level of collapse, and you end up with something that is so dense that light cannot even escape. These are, of course, the famous black holes, which you've certainly heard of. And so these are also have been observed and extremely interesting objects. So that's the result of that's the death of a massive star. And the part of this process, the part of the story, there's actually many, many threads in the story, but the part I'm going to talk about is right after the collapse, just as the compact remnant is being formed, there is this enormous burst of neutrinos. And it lasts 10 seconds or a few tens of seconds. And this bright flash of neutrinos, we can actually observe it in neutrino detectors that we have running around the world. Okay, and that's basically what I'm up to. That's what my part of my research is. And I can also mention that you've probably heard of ripples in space-time gravitational waves. That was a Nobel Prize a few years ago. That from very energetic, cataclysmic cosmic events, it actually perturbs the fabric of space-time. This is a prediction of general relativity, which is borne out beautifully in the observation that can actually be observed in very sensitive detectors that are looking specifically for this. These are gravitational waves. And so you can also see the death of a star and the subsequent explosion in the gravitational wave sequence, which I'm not going to talk about explicitly, but this is something that would happen at the same time as the neutrino burst and is potentially observable. Okay, and back to the neutrinos. So now let me talk about the neutrinos from the core collapse. In astrophysics generally, neutrinos having only weak interactions, this is actually kind of both a blessing and a curse. And this is actually not AI generated. This is from a Google image search for the prompt ghost escaping. This is apparently somewhere in Germany. Neutrinos, because they interact so weakly, they just go right through matter. They will bring information from inside very dense objects where photons would never get out. And this is the case for a core collapse. You've got this super dense thing, neutron star being formed, potentially black hole being formed, very, very dense matter. You're never going to see photons from that inner region where there's all this exotic cataclysmic stuff happening. The neutrinos, because they just zip right through matter to a very good approximation, are able to escape. And if we can detect them, we can use them to tell us about what is going on in those really exotic places. And so that is the blessing part, is that neutrinos, they bring information from areas that you could never see photons from, because it's kind of like X-rays, you could never see anything deep inside these very dense objects. And they're also not bothered by electromagnetic fields, so they just go right to you. They don't swoop around affected by electromagnetism. They come right to you from where they came from. But the flip side is, the curse part is that because of their weak interactions, you have to really make heroic efforts to detect them. You need these enormous detectors. You need to put them underground. It's not an easy thing because the interactions are so rare. You need these huge detectors. So that's the hard part. Okay, so you might ask, why do you get this big burst of neutrinos? And it turns out that 99% of the energy of that collapse is emitted in the form of neutrinos. 99%. These are events that are almost as bright as a galaxy in light. And yet there is more than 100 times more energy in neutrinos. Now, why is that? Why does almost all of the energy of this collapse basically escapes in the form of neutrinos? And there's actually a physical argument for why, which I'm going to give you, which is actually understandable just from high school physics. So you may remember I think I learned this in chemistry, actually, in high school rather than physics, but if you have gravitational potential energy, first of all, energy is always conserved. Okay, this is a very fundamental principle. And if you drop something, it starts with gravitational potential energy, and that gets converted into energy of motion, kinetic energy. Okay, so energy it doesn't disappear when you drop something. When it hits the ground, that energy is also conserved. It could go into energy that is in the form of sound or heat or something like that. Okay, but the energy is always conserved. And this is exactly what's happening. It's like a gigantic fall. It's basically the whole star falling. All the matter of the star is falling inwards. And that gravitational energy has got to go somewhere. It has to be conserved. And you might think, well, it goes into the bang, and it does, some of it does. But because that energy can escape, because it is allowed to escape, because the neutrinos which have energy can take away that energy and fly off to infinity with that energy. And they do that very quickly. Because that energy goes so quickly into neutrinos, almost all of it escapes in the form of neutrinos. So it's basically energy conservation, and 99% of it manages to escape within about 10 seconds. There's actually a brief period where the neutrinos are so dense the neutrinos are themselves trapped, which is kind of mind-boggling if you're a neutrino person. But that's a short time. And the neutrinos will get out within 10 or maybe even 10%. And they take away almost all of the energy of the collapse, which is crazy. Now, some of that energy will go into the explosion. And this is actually a field of actually computational physics, which is very vibrant. There are a lot of people working on these kind of calculations. to try to understand, some of the energy does go into blowing up the star, so basically the sound and the light in some sense, in the sense that it goes into basically throwing all the star's matter into space and making photons of different kinds. And this is actually understanding how that works in detail is a complex computational problem. I don't work on it personally, but there's a rich, a community which is working on that, and they have these lovely visualizations of what is actually happening during the explosion. And the neutrinos are actually involved in this process. And so we actually do have to understand the nature of the neutrinos to understand this process. Okay, so you might wonder, how often have we seen this? Have we ever seen this before? How do we know this is all true? Is it all just theoretical? The answer is, it has been observed once in the history of humanity. This was in 1987. There was a very famous supernova that occurred in actually not in our own galaxy, but in a galaxy that's just a bit outside our galaxy, kind of one of our local friends, galactic friends. There's a large Magellanic Cloud. It's not visible here, but it's visible from the southern hemisphere. And so if you've ever gone skygazing in the southern hemisphere in Australia or somewhere, you can actually see the large Magellanic Cloud as a kind of fuzzy blob on the sky. And it's a little galaxy. And this supernova happened in that galaxy. So it's about 5 times farther away than the center of our galaxy from us. And there were about 24 neutrinos that interacted in a detector. So we saw about 24 neutrinos from that supernova in 1987. And that, of course, was a huge deal. And in fact, it's often the joke is made that there were many, many, many times more papers written about those 24 neutrinos than there were actually neutrinos. It's really, that is a huge thing. In fact, that was part of one of the, I think, an earlier neutrino Nobel Prize. And how often do we expect this to happen? So here's a picture of our local neighborhood. So we're here in the Milky Way. The LMC, the Large Magellanic Cloud, where the supernova happened, is just a little outside here. There's also a small Magellanic Cloud. Andromeda, which is the nearest big galaxy, which you can also see on a dark night pretty easily, is over here. And we expect within our galaxy and its friends in the area, sort of within a sphere over here, we expect about 1 core collapse to happen about every 30 years. Okay, so it's something that doesn't happen very often. And some people get bored. Some people say, I'm not going to spend my scientific life on that. And actually, you do want to have some other things to do other than waiting for a supernova, of course, if you're a scientist. However, what I think, that's frequent enough that it's not unlikely to happen within a career. And we should be absolutely prepared to gather as much information as we possibly can, because it's not going to happen often, right? It's something we have to get as much as we can out of when it actually happens. Okay, so when the next one happens, so we saw a couple dozen neutrinos, which is not a whole lot from the last one. The next one, we can learn all kinds of stuff, and I won't go into all of these things, but it's going to be an absolute bonanza. We now have much bigger and better detectors from what we had in 1987. We can learn how the explosion happens, what happens to the neutron star. We can actually see if a black hole is formed. And actually, this is the thing this is like my dream. So what you would actually see if a black hole is formed is you'd see a really bright burst of neutrinos for about 2 seconds. Bam, it would cut off. If the neutrinos would be inside the event horizon and we get no more emissions. So that would be actually a very clean signature, very bright burst, because those are the hotter, bigger stars that form black holes typically. And then bam, nothing.
How long do we have to wait?
No, we don't know when it's going to happen. It could be, and actually every 30 years is, it could be 60 years from now. It could be next year. We don't know. I hope so too. Yes, yes. I mean, I've already been working in this field for 30 years and haven't seen one yet in my, started after 1987, but yeah. And not only that, we can actually learn about particle physics too. We can learn about the neutrinos themselves, because we can actually learn about the properties of neutrinos, what their actual masses are. We can learn about how they, their flavors interact with each other. And we can also look for physics that is outside of our standard picking. So there's enormous amount. It's just enormous. And it's kind of, and I kind of call this a virtuous circle, because the more you know from the lab about the neutrinos, the better you can infer information about the astrophysics. The more you know about the astrophysics, the better you can constrain the particle physics. So it's really, it's a win-win kind of thing. And what we can learn is from measuring the energies and the flavors. And so just to footstep that, you know, the more you know from neutrino experiments, the better it is. And the more you know from other measurements, the better off you are. So it's a giant party. You know, if this happens, I mean, our 87A was already a party. This would be an absolute carnival. I mean, it would be fantastic. And one thing that's great about the neutrinos is that they provide an early alert, because they come out promptly within 10 seconds. The actual photons, when you actually get the bright supernova, that can be something like 10 hours later. It might be an hour later, it might even be a day later, and actually sometimes there might not be even any. All right, so let me say a little bit about how the detectors, they're made of different materials. We can make detectors of water. Usually if you have a really big detector, the material better be relatively cheap, or otherwise it's just really expensive. Water is cheap. You have to make it pure, but you can make a big detector out of water. Scintillator is a material that emits light when particles deposit energy in it. It's usually a hydrocarbon. If you want to make it big, it's kind of like a mineral oil sort of thing. And then argon, which is a gas that comes from the air, if you liquefy it, you can actually also make detectors out of that. And this is actually a picture from an American Scientist article that I wrote in 1999 on a different topic. Most supernova neutrino detectors, because of the possible long waiting time for getting science, actually are built to look for other stuff. They're actually not built only for supernova, almost all of them. They have a day job. They're built to look for, they're built to measure neutrinos from other sources like the sun, from the atmosphere, and actually from artificial sources. In fact, this is an example of the first so-called long baseline experiment where neutrinos are generated. This was a lab in Japan and was sent to a water detector on the other side of Japan to measure the properties of neutrinos. So that's the day job of most of these detectors. But they're actually also able to measure supernova neutrino bursts. And this is an example. This is kind of an example of one of the main kinds of detectors, and it's one of the ones that I work on. And actually, I think this is what I talked about when I gave, I think, a talk in this series, or a predecessor to the series, was on a detector called Super K, which I'm still involved in, which is a giant volume of ultra pure water surrounded by light sensors. And the way you can see a neutrino is the neutrino comes in, it bashes into something. Okay, only a very few of them do it, but if you do, you get a charged particle, and this makes a kind of shock wave of light. So this is a picture of a sonic boom in a fighter jet, but it's kind of like that. It's a shock wave of light, and you can see the light then on photosensors that are covering the inside surface of the detector. So this is kind of one of the canonical main neutrino detectors. Just a little bit more about Cherenkov radiation. This is the kind of shock wave that you get. And actually, if you see pictures of nuclear reactors that are glowing, that blue light is that kind of radiation, basically from charged particles that are making these little shock waves of light coming from the reactor cores. And so you can see kind of the projection of these giant rings of shock waves of Cherenkov light that come from the neutrinos from actually many sources, not only a supernova. And Super K is the detector I was mentioning. This is 50 kilotons of ultrapure water in a volume. The inner surface is covered by these photosensors, which are these giant things that are about that big. And there's 13,000 of them, and it's about 1 kilometer underground. So you drive in. This is actually our lunchroom over here. You drive in about 1 kilometer. It's an active mine. In fact, this was built originally as it's actually a very ancient mine in Japan. And this is what it looks like inside. This is a picture from 1996, and actually this is on a cover of American Scientist. In fact, this is that article, I think, was 98 or 99. And these are these giant photosensors. And if we have a burst of neutrinos from our Milky Way, Super K, Super Kami Kondo, this detector will see about 10,000 neutrinos within about 10 seconds. A gigantic burst. And here's actually a little animation. This was made by a student of mine. So what this is here, each little dot is the one photosensor, and if it's lit up, that means it got some light. And this is a kind of projection. This is a cylinder. You take the top and bottom and you fold them out, and you cut down the side and you fold it out. So this is showing the sides, the walls of the detector, and the top and bottom. And when I click, you're going to see in real time what it would look like if a supernova went off. Okay, so I'm going to click here. It's going to start off here. That's working. Oh, there you go. Boom. So the whole thing would just light up like a Christmas tree for about 10 seconds. And this would be absolutely amazing. And this is compared to 24 neutrinos from 1987. So it would be enormously huge number. It would be, you can imagine the number of papers that would be written about this. Okay. And one other thing I just want to mention is that the neutrinos actually can tell you where the supernova is on the sky. Which, of course, if you're an astronomer, you desperately want to know that because you want to know where to point your telescope. Even if the light isn't going to show up for a while, you want to know where to look. And some of the neutrinos, when they come in, they kick electrons forward. And the electron remembers who kicked it and where it was kicked from. And if you actually look at the ones that were kicking electrons, you can actually see on the sky where the supernova was. So this is actually something that this is actually an active component of my research, is actually using different detectors, how to look back and figure out where the supernova is. And you have to do it fast too. It's actually a hard problem. Now, the next generation, there's actually a detector under construction now called hyperkamiokanda. I'm actually not involved in it. It's about 8 times the size of Super K and will have 80,000 neutrons. So enormous. It will be absolutely amazing signal. I'll go through some of the other detectors. There is another kind of detector at the South Pole. If you've heard about neutrinos, you might have heard of this experiment. It's called IceCube. There's also a counterpart in Mediterranean, which maybe you might prefer if you prefer sun to ice. But this is a kind of detector. That's what their building looks like. This detector is made of these long strings of photosensor that are embedded into ice, and it actually covers a kilometer cubed of material. So you can imagine you got a huge number of neutrinos interacting there from a supernova. And this is actually mostly built, this is actually a really high energy neutrino. There's some neutrinos that come from the cosmos that are extremely high energy, make these enormous bright splashes of light. Supernova neutrinos are much smaller. There's lots of them, but they're like little tiny dim flashes. But you get so many dim flashes in 10 or 20 seconds that this kind of detector can actually see a burst from supernova. So this is actually a really, really cool application of this detector, which was actually not only built for a different kind of neutrino. I'll mention the scintillation detector. There are a bunch of different kinds of this detector. They tend to be smaller because, as you can imagine, oil is more expensive than water. So they tend to be, instead of being 50 kilotons, they're more like 1 kiloton. And this is a clear mineral oil kind of thing that will make a flash of light when a particle goes through it. And these detectors will also see thousands, up to thousands of neutrinos when a supernova happens in the galaxy. And then there are detectors that are made of liquid argon. And actually, this is my main research activity is related to this kind of detector. These are detectors that are actually kind of completely different detector. They don't use phototubes in the same way. What happens is you get a particle that makes a little track, and then it weaves, it kind of smacks off the electrons where it's leaving energy and makes a little image. And then you can take that charge and then you can read out that charge and you can actually make a little image of what the neutrino produced. And it's actually fine-grained detail. These are really entrancing in their fine-grained detail that you can see. And there's one of these that I work on, which is a big ticket US effort in South Dakota. So it's being built underground in South Dakota. Its day job is also to look for neutrinos that are produced in a beam. So it has a whole day job that is different from supernova neutrinos. And this beam produced at Fermilab in Illinois goes underground, and you see the neutrinos here. But if you have a supernova, you also see the burst of neutrinos in this detector. And so that's actually what I'm personally working on. And here you would see thousands of neutrinos from a Milky Way supernova. And that's what I'm waiting for. I have other things going on, but that is one of the things I'm waiting for. And so the really entrancing thing is that you get, instead of just a flash of light or a ring, you get these really exquisitely fine-grained, detailed tracks of what the neutrino does after it smacks into an atom. And I want to say that, and so these are the big new detectors in the world that are either turning on now or will be turning on within the next 5 to 10 years. There's Hyper K, which I mentioned, which is the upgrade to Super K in Japan. There's Juno, which is a 20 kiloton scintillator detector that's just turned on in China, is actually getting first results now. Not neutrinos, but they're actually looking at neutrinos from nuclear reactors. And then there's DUNE, Deep Underground Neutrino Experiment, which is the argon detector in the US, which should be turning on in the next 5 to 10 years. And these are actually, in their day jobs, are actually competing with each other. They're actually trying to see, learn about neutrino properties. And there's it's a friendly global competition to measure neutrino things first. Okay, that's the way scientists, like humans, are always competing with each other. But I have to say that for the supernova, these 3 kinds of detectors see different parts of the supernova burst. They're actually completely complementary. Hyper K sees mostly antineutrinos, actually. Neutrinos come in neutrinos and antineutrinos. Hyper K sees electron antineutrinos. This one also sees antineutrinos, but also can see all the flavors in a lower rate way. And DUNE sees electron neutrinos. So these are different parts of the signal. So it's kind of like seeing different colors. It's like seeing different colors, different wavelengths of an image. It's, you get a fuller picture if you can measure all of it. So they're extremely complementary. And it's kind of the more the merrier situation. You want all the flavors, you want everything you can get. It's only going to happen every 30 years. It's going to be that question.
What happens if it's doing its day job when the supernova occurs?
We have to worry about that, but it's not really a problem. We just have to make sure that we have a constant trigger going on, that it's a technical issue that we have to take care of to make sure that we don't lose data during a burst, but it's not a problem.
You can disentangle it.
Yeah.
What's the lifespan of these detectors and
Yeah, great question. And actually, maybe I can go to the next one, which will show some of this. Is a little bit out of date. So this is so the supernova early warning system. It's actually something that I founded 20 years ago or so, which is a network of detectors that are sensitive to supernova neutrinos. This is a picture from, I think, probably about 6 or 7 years ago. And the detectors tend to run, some of them run very long, decades. Like Super K started in 1996 and is still running, will probably run at least another 5 years. And so so this is a snapshot of what the landscape looked like 5 or 6 years ago. So Super K is still running. CAMLAN, this is a scintillator detector, about a kiloton, is actually still running, but in a different mode, and could still have some supernova sensitivity. So its lifetime is, so the lifetime, it could be a decade, it could be shorter. Diabei, this is one in China. This is off. This finished its mission. Its day job mission was to measure reactor neutrinos. It actually did a fantastic job, and now it's done. LVD has actually been running for, I think, more than 30 years. This is a Gran Sasso in Italy. That one is coming to the end of its life. It hasn't turned off yet. Actually, it's only doing supernova monitoring now. Worksino is finished. That also finished its mission. That ran for probably 10 or 15 years. This one, Halo, this is actually a dedicated supernova detector, but it's very small, and it runs in Canada, and it's still running, and probably will run for a long time. It's small and it's cheap, so it can run for a long time. If you want something to run for a really long time, it has to be cheap. IceCube at the South Pole is also still running, and this probably will run, I would say, at least another decade or so. So it depends. The shortest timescales are probably 5 to 10 years, but some of them can run for decades if there's funding and if there's still it has to have either funding or other physics motivations. We're upgrading SNOOS. We're coming into an era what we call SNOOS 2.0, and actually there's a much broader range of experiments. You can see some of them here. Some of those are the same ones on the previous slide, but there's actually new ones, and we're trying to make it faster, increase the performance, and make a better infrastructure for what. And in fact, you can sign up. You can sign up. That we actually have a network of amateur astronomers, and anybody can sign up. And you could join the alert list. And to actually find the supernova is it's not necessarily easy. And there's a possibility that amateur astronomers, who are actually, some of them are absolutely amazing, really know the sky very well, may actually be able to find, we can point with the neutrinos, but not that well. It's still a large swath of sky that we would point to, that there would still be lots of possibilities. And the amateurs are, might have some capability to actually zoom in and find the supernova first. So let me leave you with this. The neutrinos, they're coming. And you can think of it this way. The far side of the Milky Way is 650 light centuries away. That means that in the Milky Way, 2,000 core collapses have actually happened already in 650 centuries, and the neutrinos are coming. They're on their way. It's going to take 650 centuries for them to get here, but they're on their way. We just have to be ready to catch them. And maybe one very final thing is, and this got a lot of press several years ago, Betelgeuse is a star everybody's seen. It's a kind of reddish star that's one of the shoulders of Orion. It's quite nearby. It's about so it's not very far away, 600 light years, and it's a red supergiant, a very massive star, and this is the type of star that is very likely going to blow up in a supernova at some point in its life. And there have been lots of recent episodes where the luminosity of Betelgeuse has been dimming and brightening, which has caused some people some consternation. Oh my God, is it going to blow up? And so the answer to that is probably the dimming and brightening is probably nothing to do with whether it's going to blow up or not. That's all stuff happening very deep inside the core, but it will likely blow up sometime in the next 100,000 years, and there will be literally 25 million neutrinos and super K still running at that time. And so it could be tomorrow. But what our job is if it is tomorrow, we have to be ready. So that's what I will leave you with. Just the summary: the sky from underground, the next birth of a neutron star or black hole in the Milky Way will be heralded by a giant burst of neutrinos. We're going to be ready with our vast underground vats of liquid. You could be the first to know, so you can sign up. This is Dorothy looking for supernova. And future detectors with a bigger, richer signal, more flavors, more colors, are going to open us to a colorful world of science. So I will stop there.
Talk about neutrinos changing color.
Yeah, so it's something, they have a property that we call flavor. Actually, that's a whole deal. They come in these three so-called flavors, and I very briefly showed them. It's the electron, mu, and tau. It's the same as the flavors of the three charged electrons, so the electron and the heavy electron, muon, and then the tau. And so we have electron, muon, tau flavored neutrinos, and also anti-neutrinos. So there's actually 6 kinds of neutrinos. But the neutrinos can actually, as they travel, change from one flavor to another. And that can only happen if neutrinos have mass. In fact, that's how we know neutrinos have mass. And it was actually the topic of the American Scientist article from 1999 that I wrote. And actually it was Super K that really showed that for the first time, that it's possible neutrinos from the atmosphere are changing flavor from electron to muon, or muon to tau, as they travel through the Earth, and we're able to measure the flavors in Super K and show that they are changing flavor consistent in with having a non-zero mass. So we now know they have, but not zero.
You talked about a black hole formation is effectively trapping neutrinos. Doesn't that create some sort of pressure that counteracts the collapse, or how is that going on?
That actually does when the neutron star is formed. Actually that you get it's what's called when the neutron star is formed, the neutrinos are actually gone. The neutrinos mostly leave. So it's an electron and a proton that squeeze together to make a neutron. And then you have basically a whole bunch of neutron gas. That, a bunch of neutron matter. And there's what's called the degeneracy pressure, which is fermi particles that have spin can't heat each other, this Pauli principle. So you have a pressure that counteracts the squeezing together of the neutrons. So there is such pressure. And that's what happens if the mass, the total mass of the neutron star is too large, if it exceeds the threshold, then the gravitational pull will exceed the degeneracy pressure, and then you get the black hole. So the degeneracy pressure of the neutrons is cannot hold up the neutron star.
But I thought you said you were waiting for a signal where the neutron flux will effectively just.
Neutrino flux. And so yeah.
Yeah, sorry.
So yeah, so you make the neutron as the neutron starts being formed. So actually you get an initial spike from the neutrinos that are emitted when the neutrons are actually formed. And that's a brief spike. And then you get, it actually is neutrinos that come from thermal emission actually. It's a different process. But they do get trapped eventually.
I probably said the wrong thing. I meant, is there a neutrino pressure?
That is folded in, but it's also not going to, it's not going to be dominant over the gravity. Big definitely concern. Yeah.
You said that neutrinos arrive before photons, they actually go faster than speed of
No.
light.
No, they don't. It's that the photons are trapped in the star, and so it takes them a while to actually get out of the star. Yeah. No, they actually go a tiny bit slower than the speed of light because they have mass. And in fact, that's how we can tell that they. It's one way of measuring the mass of the neutrinos. If you can actually look at the pulse of neutrinos and see it's a little bit delayed. If the lower energy neutrinos are a little delayed with respect to the higher energy ones, then you can actually learn about neutrino mass. It's a tiny play.
Yeah, so you said we're being bombarded with neutrinos.
Yep.
currently
Yes.
For a second.
It's muons. It's even more neutrinos. If you put your hand up to the sun, it's like 10 trillion neutrinos per second. Trillion, yes.
So do we think where are they coming from? Coming from the sun?
Most of them are coming from the core of the sun. They're produced in fusion processes. Yeah.
We have a couple of online questions.
Oh yeah.
The first one is, when neutrinos are produced in a supernova, charge and lepton number must be conserved. What production mechanism does this?
It's actually mostly a neutral current production. So it's actually, this is a question about the sun or a supernova.
It says in the supernova.
Supernova. So it's actually mostly neutral current scattering of leptons and antileptons, or quarks and antiquarks is actually the dominant process, the thermal process. There's a bunch of them, nuclear Bremsstrahlung and so on, but it's mostly neutral current, which means that you get neutrinos and antineutrinos produced equally. So the verse is actually almost equally populated by neutrinos. The lepton number is conserved.
Okay. The other question was, what is the ultimate fate of all the neutrinos being emitted? What happens to them eventually?
They go to infinity. In fact, that's actually a very interesting question, because we are actually in a bath of neutrinos that were produced in ancient supernovae. In fact, that's one of our goals in Super K actually, is to measure the diffuse, what's called the diffuse supernova neutrino background, which is the kind of sum of all the neutrinos that were ever emitted by all the supernovae in the universe that have ever happened. And that should be there. In fact, we're pretty sure that it's there, but it's just a very low level. And so what we're actually trying to do is actually detect that flux. And it's something in Super K, we'd only get a few per year. Like from a nearby burst, we get 10,000 Dan all in 10 seconds. But if we're looking for this diffuse flux of neutrinos from ancient times, we only expect maybe a handful per year or less. So that's really hard to do, because you get all kinds of things can take that signal, and so it's a really hard technical problem to see it.
Any other questions? All right, thanks so much.
I think those two on.